for the Advancement of Science, Section E1, with the collaboration of Physics Society of University of Jayewardenepura. I warmly welcome our guest lecturer, Dr. Dulsha Abeywardana, of the Department of Electrical, Computer and Software Engineering in University of Auckland in New Zealand. And I also welcome all our lecturers and all the students to the webinar today. I hope everyone is eager to know more about the way on superconductors and the postgraduate opportunities in New Zealand. Without further ado, I would like to call upon Dr. Vasanthi De Silva, the President of Sri Lanka Association for the Advancement of Science, Section E1, to introduce the speaker today. Madam.
Yes, thank you, Arishi. So first, I would like to thank Dr. Dulsha for accepting my invitation on behalf of class Section E1, as well as the Physics Society, University of Sri Jayewardenepura. So I will brief about Dr. Dulsha before we start the talk today. Dr. Dulsha is currently working as a lecturer at the University of Auckland in the Department of Electrical, Computer and Software Engineering. She has been teaching at the University of Auckland since completing her PhD in 2017. Prior to that, she was a lecturer in the Department of Physics at USJP since 2019. So upon completing her bachelor's degree in Electrical and Electronics Engineering at the University of Auckland in 2005, she returned to Sri Lanka, where she has worked at Motorola, London Stock Exchange Group, and the Dialogue University of Maritime Mobile Communication Research Lab. Her research interests are power electronics, supercapacitors, wireless power, electropermanent magnets, and STEAM education. So Dr. Dulsha is also secretary for both IEEE Women in Engineering New Zealand North Section and the IESL New Zealand chapter. So today she is talking on the power of supercapacitors and the postgraduate opportunities in New Zealand. So I warmly welcome Dr. Dulsha. Over to you, Dr. Dulsha.
Thank you very much, Vasanthi, and thank you for inviting me to speak to your prestigious audience. And so let me start off by sharing my screen with you. So just double checking that you can see the screen that I'm sharing at the moment.
Yes, we can see it.
Yeah, okay. Thank you so much for that very kind introduction, and I'm just struggling to advance the screen. Try that again. Yeah, okay, so yeah, looks like it's working now. So just to give you a brief overview of my presentation, in the first half of my presentation, I will be talking about the power of supercapacitors. So an area that I'm venturing into in terms of my research. And I will be talking about capacitors in general, so revisiting some of the things that you may already know. And then introducing supercapacitors and talking about how they're different in comparison to common technologies like batteries. And then go on to talk a little bit about some of the conventional and non-conventional uses of supercapacitors. So after that, I will also spend some time talking about postgraduate opportunities in New Zealand, and a little bit specifically about postgraduate opportunities at the University of Auckland. So as it was mentioned before, so I usually like to give a brief introduction about myself. So I actually completed my school education in Sri Lanka, just like most of you, I guess. So I then moved to New Zealand, where I studied electrical and electronics engineering at the University of Auckland. And I then worked as an engineer at Motorola, as a business analyst at the London Stock Exchange Group, and then moved on to a more research-oriented career at the University of Muratua. And finally, started off in academics, actually, at the University of Jayewardenepura. So upon entering academic career, I decided to return to New Zealand to sort of start my PhD studies. And upon completing that, I've been working here as a lecturer for the same department. And as mentioned, some of my research interests include supercapacitor application and wireless power transfer and electropermanent magnet-based applications. So in general, I classify myself as, I guess, a hardware engineer. And another area that I'm particularly keen about is STEAM education, especially for young children. And I also advocate for women in engineering because we are a minority group, and I try to support people working in my profession through the New Zealand North section. And also I like to keep in touch with the Sri Lankan community. So I am involved in IESL New Zealand. So I guess all of that sort of falls under the professional umbrella of my career. And apart from that, of course, just like all of us, we have another life. So I also wear many other hats in life. I've got 2 children, and I guess like all of us, we always have to think about work-life balance as well. So that's me. So let's get started on the, I guess, the more interesting part of our presentation today. So let's, I guess, revisit capacitors. So since I've studied in Sri Lanka, so I'm fairly aware of the things that you sort of talk about while you're still at school. So I know that we've all learned about capacitors, I guess, but I'm not expecting you to remember a lot of things. So let's quickly revisit capacitors in the sense to relate it to supercapacitors. So what do we already know about capacitors? Well, we know that they store energy in the form of an electric field. So when we talk about capacitors in their most basic form, they are, we think of them as 2 conducting plates. And let's say they've got a surface area of A, which is separated by a distance D, and a dielectric material with a permittivity of epsilon is sort of inserted between these 2 materials, these 2 conducting plates. So when we connect a voltage source between the 2 plates of the capacitor, so when we provide the capacitor with a voltage, a group of positive charges accumulate on one of these plates, while an equal amount of negative charges accumulates on the opposite side of the plate. So this is all things that we know, and this creates an electric field between the 2 plates. That's how energy is stored inside the capacitor. So the capacitance, or how big a capacitor specifically is dielectrical, the surface area of the conducting plates divided by the separation distance. So by playing around with these three parameters, we can change the capacitance. So if we wanted a larger capacitance, for example, we can play around quite easily with this surface area and the separation distance. So, so bearing that in mind, I want to briefly also talk about what actually happens when we charge and discharge a capacitor. So let's start off, I guess, talking about the charging aspect of a capacitor. So when we connect a voltage source, so a voltage starts to accumulate on the capacitor plates because a current starts to pass through the circuit. So initially, the current is quite big. And as the capacitor voltage starts to gradually increase, this current actually starts to decrease more or less proportionally, so that eventually the capacitor voltage actually reaches the same voltage as the source. And that's when a current no longer flows through this circuit, and we say that the capacitor is actually fully charged. So the time that it actually takes for this process, for a capacitor to fully charge from having no charge accumulated on its plates at the beginning, and it is governed by the resistance and the capacitance that is present in this electrical circuit. So as you can see, how fast the capacitor charges depends on how big this resistance is and how large the capacitance is. So if the resistance, for example, is small, the time constant could be smaller. And also if the capacitance was bigger or smaller, we can see how the time constant increases or decreases proportional to that. So if we look at the actual charging profile of a capacitor, so the voltage actually increases in this sort of pattern, so that it gradually increases and evens out and reaches a final voltage. And this happens at the time where it's equal to 5 times the time constant of the resistor capacitor circuit. So at this 5 time constant mark, we also know that the current actually decreases. So current starts off being at its maximum when the capacitor is not charged, and the current then gradually decreases and goes down to 0. Yeah. So similarly, when we discharge a capacitor, the voltage starts off being at its maximum previously charged value and decreases down to 0 at this 5 times the time constant mark, 5 tau. And similarly, the current starts off at its maximum and reduces all the way down to 0 at 5 time constants of the resistor capacitor circuit. So what I sort of wanted to highlight here was that one thing is that a capacitor simply needs to be provided with a current, let's say through a voltage source, to be charged. And this property is actually quite useful in comparison to other energy storage devices such as batteries. So we don't actually need special charging circuitry to charge a capacitor. So how are supercapacitors different and also in some ways similar, in many ways similar actually, to capacitors? So supercapacitors are basically very large, capacitors with very large capacitances in comparison to the regular capacitors that we use to, which generally go up to about 1,000 microfarads at most. So how are supercapacitors actually physically different is that they use activated carbon electrodes, which are actually porous materials, which allows us to increase that surface area of the conducting plates so that we can actually increase the property A that we talked about right at the beginning. Right? So this also, supercapacitors are constructed in such a way that the distance between the electrodes are kept to a minimum so that the property D is actually minimized as well. So this allows for a much larger capacitance C, and a supercapacitor actually has what we call charge collectors connected to the electrodes, and the electrodes are submerged in an electrolyte which has ions which get ionized when we actually supply the two plates of the capacitor with a potential difference between them. This causes the ions in the electrolyte to be attracted to either side to create that, to basically store energy within the supercapacitor. So because the capacitance actually in this case is quite large in comparison to regular capacitors, the amount of energy that is stored is actually much bigger than what is possible with your average capacitor. So the amount of energy stored in any capacitor, not just supercapacitors, is basically governed by this equation, which is half C times the voltage squared. So C being the capacitance. So this increasing this value C actually allows us to store a much larger amount of energy inside supercapacitors, which is one of the most useful properties of supercapacitors. So there are several types of different supercapacitors, and I'm not going to go into detailed information about their construction and so on. So we get what we call the electric double layer capacitors, the pseudo capacitors, and then we get the hybrid capacitors, which is as the name speaks, it is a hybrid between these other two types of capacitors. And the main difference between these different types of supercapacitors is the way that the electrical energy is actually stored. So hybrid supercapacitors actually have one electrode which is similar to the lithium-ion batteries, so that we try and harness some of those useful properties of the lithium-ion batteries. So when we talk about supercapacitors, some of the striking properties of supercapacitors that we try to make use of, and of course, there are some downsides as well. I will talk about it when we get to it, when you talk about supercapacitors, but some of these properties can be quite useful, making supercapacitors an interesting way forward in the energy storage domain. So one of the main things is that they have capacitances, which is up to about 1 million times bigger than the average capacitance of the capacitors that we generally use in circuits. And supercapacitors, like any other type of capacitors, have a virtually unlimited number of charge and discharge cycles, which is one of the main properties of supercapacitors in comparison to batteries, where you can only have a certain number of charge and discharge cycles, and then it's time for the battery to be discarded. And then supercapacitors also allow for fast and straightforward charging, because you actually don't need specialized charging circuits and things like that. And they've also got a very low internal resistance. So despite having a large capacitance, the low internal resistance allows us to charge them reasonably fast, because the resistance value R is small, although the capacitance is large. And they've got really high power density. So what does that mean? Supercapacitors, unlike smaller energy batteries, supercapacitors are capable of delivering a much larger current for applications that actually demand a larger current. I guess the other main characteristic and useful property of supercapacitors in terms of the environment is that they've got no toxic chemicals involved in their construction. So some of the end-of-life disposal issues that we have with rechargeable batteries being harmful to the environment and all of that is solved by the use of supercapacitors because they don't actually have toxic chemicals within them. One downside to supercapacitors, as with any other capacitor type actually, is the lower energy density compared to batteries. So yes, supercapacitors can supply a much higher power, but if we compare them to batteries, supercapacitors cannot store as much energy as the battery does at the moment, but the energy density levels of supercapacitors are forever increasing as new technologies and new versions of these devices start to come up. And one of the main downsides of supercapacitors is also their much lower voltage rating in comparison to the average capacitor. So if you take an electrolytic capacitor, it will have a rated voltage anywhere between about, let's say 63 volts to about 10,000 volts, for example, whereas supercapacitors are severely limited in this sense, where most of them have a voltage rating of about 2 to 3 volts. So when we charge supercapacitors, as I mentioned before, we don't actually need to do anything special. It's the same as charging any other capacitor. So as long as we have a resistor capacitor circuit connected to a voltage source, it will charge exactly like any other capacitor. So we don't need the specialized charging circuits that are associated with rechargeable batteries. So it's very straightforward and much easier to work with, especially when you're using multiple supercapacitors in arrays and so on. So in this circuit, I've highlighted the supercapacitor separately, but this resistance itself could be the internal resistance of the supercapacitor, which is usually very, very small. So just comparing supercapacitors with regular capacitors as well as batteries, which tend to sit on two ends of the energy storage device spectrum, we can see that things like lead-acid batteries, lithium-ion batteries tend to have much higher energy densities in comparison to supercapacitors, and electrolytic capacitors have even lower energy densities. So what does this actually mean? Batteries can actually store more energy, or they can store more joules of energy within them compared to supercapacitors and electrolytic and other types of capacitors. But however, supercapacitors sit in the middle of the spectrum again when it comes to power density. So what does that mean? Supercapacitors can actually deliver more power at a time. So it can deliver, for example, let's say it can deliver a power of 10 watts, for example, whereas a similar sized lithium-ion battery is not capable of delivering 10 watts instantaneously because of other limitations in the construction of the battery itself. So supercapacitors can always be thought of as a hybrid between batteries and capacitors, where some of their favorable as well as unfavorable properties are combined. So I'm not going to go into too much detail, but this table actually allows us to compare aluminum electrolytic capacitors, where you get the highest levels of capacitances when it comes to the regular capacitors. And then we have the supercapacitors. So all three of these are the different types of supercapacitors. And then we get the lithium-ion batteries. So some of the things that I wanted to sort of bring out here was that supercapacitors have these large number of recharge cycles. So we can actually use them over and over again. So we can charge and discharge and charge and discharge continuously, whereas lithium-ion batteries have a much smaller number of charge-recharge cycles. So once we sort of hit that limit of the charge-recharge cycles, we basically need to discard the batteries, whereas supercapacitors can be used for much longer. And of course, compared to regular capacitors, they have much higher capacitances, and they have really high specific power or power density compared to lithium-ion batteries, and they provide fairly high efficiencies where energy is actually not lost in the process of delivering energy from a supercapacitor. So their working life is also much higher in comparison to lithium-ion batteries and other battery technologies. So these are some of the favorable properties of supercapacitors, sort of put into context with the other energy storage devices. So I don't want to go into detail here, but one thing I wanted to sort of show you was that the internal resistance of a supercapacitor tends to stay quite constant and low, whereas the internal resistance of a battery tends to stay higher and also varies as we discharge the battery. So this is actually one of the main properties that is useful when it comes to solar energy delivery and charging, where we use what is called the maximum power point tracking, where the internal resistance is matched up with the load and some of the other properties of the rest of the circuit. So if the internal resistance stays constant, this is much easier to do. Whereas with batteries, it is a little bit harder to do that because the internal resistance actually changes as the as the battery discharges. So in terms of the voltage of the supercapacitor and a battery when they're discharging, the supercapacitor tends to discharge a lot more linearly. So the voltage will linearly decrease and the supercapacitor will discharge faster. And a rechargeable battery tends to hold its voltage for a lot longer and then suddenly die out and becomes useless until you recharge the battery again. So this is just a simple comparison of supercapacitors and batteries. So I guess the other most important thing with supercapacitors in comparison to batteries is that supercapacitors don't actually require that specialized charging circuitry, whereas batteries, depending on the chemistry, will require a specialized charging IC and additional circuitry, which adds to the cost of the actual system, as well as costs you some of the efficiency in this system as well when delivering power from the source to the actual energy storage device. So when it comes to sort of using supercapacitors or harnessing the actual power of supercapacitors and making use of these properties that we talked about, there are some typical applications where supercapacitors are conventionally used. So if you sort of look up uses of supercapacitors, one of the first hits that you will get is energy buffering. So what do we mean by energy buffering? So supercapacitors, let's say combined with any other power source like a battery, will act as a peak power delivery system. So if the battery, for example, can only supply a current of, let's say, 1 ampere, a supercapacitor combined with this battery is able to give us more power for a short period of time and allows us to buffer the energy demands of the actual application that we're powering using the supercapacitor. So this is actually a very, very common use of supercapacitors. And another common application where you see supercapacitors is in fast charging applications. Because of the much higher power density of supercapacitors, they can actually absorb energy much faster than a battery does. So the charging and the discharging process being straightforward allows us to actually fast charge supercapacitors in comparison to batteries. And this becomes quite useful when it comes to charging supercapacitors. So to put that into context, if you could charge your phone much faster, if your phone, for example, instead of having the regular lithium-ion battery had a supercapacitor based energy storage system, you could charge it much faster because of its fast charging capabilities. But of course, on the downside, your supercapacitor powered phone will not be able to store as much energy as your regular lithium-ion battery does. So another application, a common application where supercapacitors have become and are starting to become useful is regenerative braking. So when it comes to hybrid cars, we talk about how when you apply your brakes, the energy that is actually wasted in this process is actually stored in the form of electrical energy. So the common and more popular strategy is to store this energy into a battery to be used later on. And by using supercapacitors, and there's a lot of research going on in this area, to employ supercapacitors in regenerative braking, allowing them to basically be able to be charged much faster and harvest that energy really quickly. And also their unlimited charge-discharge cycles allows us to use these supercapacitor energy storage banks for a lot longer before you need to replace them compared to the regular batteries used in hybrid cars. So I guess when we talk about hybrid cars, one of the main things and the main drawbacks we talk about is the battery life. How long will the battery last before I have to replace the battery at a very high cost? So if, and it's more like when supercapacitors have reached that energy storage capacity levels, they are fully capable of being used as energy storage devices to harness the energy through regenerative braking. So these are some of the conventional uses. So some of the creative uses of supercapacitors are what I'm just about to present to you now. And I have to mention that this is not purely my work, and most of this work has been done by a large team of New Zealand researchers. And of course, like there are other researchers around the world working in similar areas in supercapacitors. So one of the creative applications, and this actually has been commercialized by a team of researchers here in New Zealand, is surge absorption technology using supercapacitors. So when we talk about surges, think about lightning and the destruction it causes to our electronic devices. So we quite often tend to protect our expensive equipment like computers and things like that using a UPS, which also has surge protection capabilities. So if a large voltage surge or a lightning surge, which is also a large voltage surge, comes through, these surges are absorbed and not propagated through the rest of the circuit, which will damage your equipment for good. So supercapacitors in this sense have been creatively used to absorb these large voltage surges from typical scenarios like lightning, where the supercapacitor will basically charge itself. So when, for example, lightning strikes, the extra energy that is delivered to your circuit is actually absorbed by the supercapacitor. And the supercapacitor needs to be selected in such a way that it has a large enough time constant or a large enough capacitance, which allows us to absorb all of the expected levels of energy in such surges, allowing for the supercapacitor to charge, but also making sure that we're not overcharging the supercapacitor. But because of the large capacitance and the large time constant involved in this case, the supercapacitors will not be overcharged, and we ensure that the rest of the circuit is basically protected by the supercapacitor, where it acts as a shield in a safe manner so that the voltage surge is blocked from the rest of the circuit and protects your expensive equipment. So this is actually the commercialized product that they've developed with Thor Technologies in Australia, which is currently in circulation in the market. So another creative application where supercapacitors have actually been used is for rapid water heating systems. So I know this is not a problem specifically in Sri Lanka, where hot water is not required, but in cold climates like in New Zealand, we tend to rely more on our hot water systems, especially during the cold months in winter. So quite often what we find is that the water does not heat up immediately because it takes time to heat up the column of water that comes through your tap. So as soon as you open the tap, we all are guilty of of wasting a certain amount of water because the water isn't warm enough for us to actually use. But supercapacitors have actually been used in this sense, where an extra amount of energy is stored in the supercapacitors and held there. And when we open the tap, the supercapacitor actually discharges itself to deliver an extra amount of instantaneous energy into your heating coil to heat your column of water that goes through the tap, so that you actually heat up your water much faster and allows you to waste less water in the process. So this is just another creative way that supercapacitors have helped us to stop the wastage of water. And another application where supercapacitors have been used in the renewable energy domain. So in this case, we've actually used solar energy. So directly connecting renewable energy sources like solar panels to supercapacitors to charge these supercapacitors up as the solar panel directly powers the lighting system, for example. So the work here was conducted with LED lighting, which is by default expected to be driven by a DC voltage source, making it really easy because renewable energy such as solar panels provide us with this DC power already. So charging the supercapacitors up in series with the LED lights, we've actually managed to charge the supercapacitor at the same time that we illuminate the light. And once the supercapacitor has been fully charged, we disconnect this supercapacitor from the renewable energy source, and a lot of things happen in the background to connect another supercapacitor so that we go through an array of supercapacitors, charging them periodically. And the supercapacitor that was fully charged continues to independently power your lighting device. So these things this technology has been actually quite useful in off-grid power systems where mains power is not available and you need to quickly set up an off-grid power system, especially if it's using DC power such as LED lights and other DC appliances. This technology has actually been tried and tested and is going through its development stages to directly power DC powered appliances without the need for battery storage for renewable energy sources. So another, I guess, a little bit more technical and electronic oriented application where all of this actually started out was the low dropout voltage regulators, which have an efficiency by default due to their actual circuit arrangement. the efficiency is governed by the output voltage over the input voltage. So if the difference between these two is quite big, you can expect the efficiency to be much smaller. So here we have employed a supercapacitor to absorb the difference between the source voltage and the actual input voltage into the voltage regulator, so that the efficiency is manipulated by absorbing the extra voltage into the supercapacitor. And then once the supercapacitor is fully charged, we actually remove the voltage source, so that we are actually not drawing power for the entire period of time from the voltage source, to therefore increase the efficiency of these voltage regulators. So the process, again, just like with the LED lighting system, this process repeats where the supercapacitor is connected and disconnected regularly from the voltage source to increase the efficiency of power delivery from the source to the load at the output end. So bear with me if it was a little bit too technical, but this is one of the earliest applications that was developed using this technology. So, like I said, these are some of the creative ways that supercapacitors have been used. And of course, there are so many other creative ways where supercapacitors can be used to harness their capabilities. And there's quite a lot of research going on here in New Zealand in that area. So the possibilities that are associated with this technology is actually limited if you sort of get your creative brains working. So I guess that concludes the more technical part of my presentation, and I guess helps us to move on to talking about postgraduate studies in New Zealand. But maybe before I move on, I like to sort of pause to ask if anyone's got any questions about the technical part of the presentation. Do we have any questions at all, or do you want me to sort of move on? I'm not sure if anything's coming up on the chat, but I will move on. And if we have any questions, I'm more than happy to discuss it at the end of the presentation as well. So postgraduate studies in New Zealand. So for quite a lot of us, we always think about, once we've completed our undergraduate degree, maybe work for a few years, we think about where can I go for a postgraduate degree? What are my opportunities in the area that I'm interested in, and so on. And also maybe for some people, it's also about making change in terms of where they live, long-term migration and things like that. So let me tell you a little bit about what happens here in New Zealand, and maybe New Zealand may be the right choice for you or maybe not. So let me start off by where New Zealand is. So I'm pretty sure all of you are aware of where New Zealand is. So here's Sri Lanka, and here's New Zealand. So New Zealand is a little bit bigger than Sri Lanka. So on average, it's about 8 times larger than Sri Lanka in physical size, but it's not as densely populated as Sri Lanka. And we're about 11,000 kilometers away from Sri Lanka. And these days, with our borders closed, we seem to feel that distance a lot more than we used to. So it's roughly about a minimum of a 14-hour flight away from Sri Lanka. And we don't actually have any direct flights from Sri Lanka to New Zealand. So quite often we need to at least have one stopover in some part of Asia, or possibly up here in Dubai. So that's where New Zealand is. And New Zealand's like you're probably aware of some of the major cities in New Zealand already. So New Zealand is also called Aotearoa in Maori, and Maori are actually the indigenous people of New Zealand. So for those of you who may be rugby fans, if you've seen the All Blacks team do the haka, that's a cultural practice that comes down from the indigenous people of New Zealand. So New Zealand has 2 islands, and this is the North Island and the South Island, very creatively named. And Wellington down here is actually the capital of New Zealand. So it's right at the bottom of the North Island, and it is the windiest city in New Zealand. And then we've got Auckland, that's where I am from. And Auckland is actually the business capital of New Zealand and also the largest city in New Zealand. So it's also the most densely populated and it's also the most multicultural community in New Zealand. So then we've got major cities like Auckland, Wellington. You may have heard of Christchurch, which is down in the South Island. So then we've got Hamilton, which is the 4th largest city. And I've just marked all the main cities in New Zealand. And I have to say, New Zealand is not as cold as people expect it to be. When I came here, I thought it was going to be snowing half of the year. It never, ever snows in Auckland. And the population of New Zealand is 5 million. And you can see how much smaller the population here is in comparison to Sri Lanka, for example. And most of this 5 million, about 1/5 of this 5 million tends to live in Auckland and its surrounding areas. So when we think about New Zealand as a Sri Lankan, the first thing that I think about still is Anchor Milk. And I guess these days, this lady is probably one of the most popular political leaders, Jacinda Ardern, the Prime Minister of New Zealand. We also think about kiwi birds, I guess the Maori indigenous people. And then for the sports fans, I guess the Black Caps and the All Blacks teams, the cricket team and the rugby team of New Zealand. So moving on to universities in New Zealand. We have 8 universities scattered through New Zealand. So we've got the University of Auckland, and that is the top ranking university in New Zealand. And the current world ranking for the University of Auckland is 85. And Auckland University actually offers all major areas of study, which includes medicine, engineering, law, business, arts, and so on. So the only thing that the University of Auckland does not offer is dentistry. Then we've got the University of Otago, one of the really, really old universities in New Zealand as well. So the University of Otago is the 2nd ranked university and also the only other university in New Zealand to actually offer medicine. And they're the only ones who actually offer dentistry. And then we've got number 3, Victoria University, which is in Wellington. So number 4 is the University of Canterbury. Some of you may have heard of the University of Canterbury, which is also a very popular university, which is located in Christchurch. And then we've got the University of Waikato in Hamilton at number 5. Number 6 is the Lincoln University, again, located in Christchurch. And some of you may have heard of the Massey University, which is located in Palmerston North mainly, but they've also got campuses up in Auckland as well. And then we've got AUT, or the Auckland University of Technology, which is basically located across the road from the University of Auckland. So we tend to be rivals with AUT, I guess, because we're just across the road from each other. And so these are the only universities in New Zealand. And I have to also say that the rankings are the overall rankings as a university in comparison to the universities across New Zealand as well as the rest of the world. But some of the universities actually are stronger in certain subject areas than others. So it is important to make sure that based on the area that you're interested in, make sure that that university is generally stronger and well facilitated for the area that you want to study. And I want to actually highlight this particularly, that these are the only universities in New Zealand. And I quite often come across students being misled by quite a lot of visa agents who would say that, there's a university that actually offers master's programs or master's degrees here in Auckland. And please make sure that if you're signing up for a university program, it is from one of these 8 universities, and be aware of all those non-university grade institutions. And we do get a lot of those as well. And some of them actually offer good quality degrees, but make sure you do your ground research before you commit to some of the postgraduate degrees that are offered. And I'm sure most of you are aware of the basic differences here. So the highest level of qualification that you can actually obtain is a PhD degree, or a Doctor of Philosophy, as it's formally called. So this is a purely research-based degree, and also tends to be a general requirement if you're thinking of following an academic career pathway. So for example, if you want to get into teaching or lecturing, you want to sort of make sure that at some point in your career, you will obtain a PhD degree. And also some of the research institutions in the research world tend to expect you to be specialized in a certain area by obtaining a PhD degree. But if that's not what you're thinking about, and also people with PhD degrees are quite often employed in industry as well, but sometimes your scope may be a little bit more limited if you have a PhD and are looking for an industry role. And then we have the master's degrees. So quite often we come across what we call the coursework-based masters or the taught master's degrees. So these are programs where you will actually go through a number of papers, and you will take a number of subjects where you will be able to further study into multiple areas that you're interested in to sort of learn a little bit more. And then we also have what we call a research master's, which is like a mini PhD, where you need to actually do your master's on a certain topic, and you will be formulating a thesis at the end of it. And quite often these research masters don't expect you to take any other coursework or any other subjects. So you will be dedicating all of your time to your master's project. So quite often with the taught masters, you may have projects in project-based courses involved as well, but these are much shorter projects in comparison to a research master's project. And a research master's is usually required, but sometimes not mandatory if you want to move into doctoral studies. And then the next level down from there is the postgraduate diploma, or what we call a PGDep. So this is basically an option that quite often students tend to take if they've followed a 3-year degree program and are not going to follow an honors program. Like I guess in the Sri Lankan terms, you're not doing a special degree. You're doing the regular 3-year science degree. You could then sign up for a postgraduate diploma, which is usually a 1-year-long qualification and an alternative to your 4-year honors degree. And then in New Zealand, we also offer what is called the bachelor's honors degree for people who have followed a traditional 3-year undergraduate degree, and then based on your performance in that degree program, you're offered an extra year of honors. And like for local students, they can obtain a scholarship to follow their honors here. So this is not really so much of an option for the international students, but these three are generally options for the international students. But I would probably say perhaps a master's, one-year master's might be a better idea if you are granted entry than following a postgraduate diploma and then trying to move into a master's program. But the requirements might be different based on the institution as well. So let me sort of now talk a little bit more about doing a master's degree at the University of Auckland. So we actually have a range of master's degrees ranging from 1 year to 1.5 years to 2 years of full-time study. Of course, if you go part-time, this duration is doubled. So you can generally enter into the master's program with a bachelor's degree or what you call a bachelor's honors degree or a postgraduate diploma. So if you're aiming to follow through to a PhD afterwards, you will need to choose between, a research master's as opposed to a master's by coursework or a taught master's. So you will also be required typically, so this is the University of Auckland requirement, you will be typically required to have a GPA or GPE, which is the grade point equivalent, calculated based on your grades, of 5 out of 9 if you want to enter a master's degree. But some programs specific to their faculty may require higher scores. I know that for the Master of Engineering Studies program, which is the taught master's program in the engineering faculty, you need to have a GPA or GPE of 4 or above. So the requirement is slightly lower than with the general requirement. So you need to have this level of GPA or GPE if you want to get into a Master of Engineering Studies. And then we come to doctoral degrees at the University of Auckland. So this, like I mentioned before, is a purely research-oriented degree where you will actually develop a lot of skills that are knowledge-based skills, transferable skills, as well as specialized research skills. And when you sort of venture into a PhD, you tend to specialize in quite a narrow area and you become an expert in that area. And you will be preparing a substantial thesis. Depending on the faculty, the size of your thesis will also vary. And it needs to be based on your original research that contributes significantly to the advancement of your own discipline. So you will need to work with at least one PhD supervisor, and quite often you will find yourself working in a larger research team led by one or a group of academics. And at the University of Auckland, we offer PhDs in about 100 different subjects. And to get into a PhD, you need to have one of these requirements. So you need to have completed a postgraduate bachelor's honors degree. So basically a 4-year degree with a first class or a second class upper division honors, or a master's degree with first or second upper level honors in the same or a related field of the doctoral studies that you're going to enter into. So you need to have completed a master's level qualification with a GPE of at least about 5.5 out of 9 if your qualification is from an overseas institution, and the previous requirements are for those of you who would have studied at a New Zealand institution. So we talk about PhDs, we talk about postgraduate, and like any of us, the next thing we think about is, can I get a scholarship? So the University of Auckland actually does have few scholarship opportunities, especially at doctoral level. So at master's level, unfortunately, there is the University of Auckland Research Master's Scholarship. So if you go into a research-based master's, yes, you can obtain a scholarship if you are a local student, unfortunately. But however, there are other pathways into getting a scholarship, which I will talk about next. So these are scholarships that are administered directly by the university. So then we have what is called the University of Auckland Doctoral Scholarship, which is available to both local and international students. So this scholarship is generally about, at the moment, it is at 28,800 New Zealand dollars. And you don't have to pay tax on this. So all of this money actually comes as a stipend. So you're not expected to do any extra work. So it's basically a stipend paid to you for carrying out your PhD research to be able to complete that successfully. And in addition to this, your compulsory PhD fees will also be covered by this scholarship for up to 3 years. And it is quite often possible to get another 6-month extension and nothing beyond that. So generally, you can expect to be funded from 3 to 3.5 years if you are able to secure a University of Auckland doctoral scholarship. So for students, irrespective of whether you're a domestic student or an international student, if you have obtained your qualification from a university in New Zealand and your grade point average or GPA is 8 or higher in this qualification, you will be guaranteed a University of Auckland doctoral scholarship. So it is not subject to availability. It is guaranteed that if you basically meet this criteria, you apply for a doctoral, you apply for a PhD at the University of Auckland, you're guaranteed this scholarship. However, if your qualification is not from a New Zealand university, you will still be considered for this scholarship if you're a high achieving student. And but the scholarship is not actually guaranteed as it is for a student with a local qualification, but high achieving students will be considered, and you're actually automatically considered for this scholarship when you apply for a PhD. And once, when they process your application and inform you of the decision, you will also be informed whether or not you were granted the scholarship. So if you want to find out a little bit more information, I've just included a link which will help you understand and give you a lot more information than I've actually put out here into the presentation. So if you're unable to secure a University of Auckland doctoral scholarship, there are some other scholarships that are available to international students. There are some government scholarships that you can apply for as well. So you can actually apply for these, if I'm not mistaken, even after you commence your doctoral studies at a New Zealand university. But I have to mention that these are quite limited. And there are things like the Commonwealth Scholarship and so on, which you may also be aware of. And of course, there are ways that you can support yourself from a scholarship through the Sri Lankan government as well, which isn't a lot, which is probably not as many, but I think you would know more about it than I would. And another approach is to basically communicate with academic supervisors who actually actively work in the areas that you're interested in with an up-to-date CV and express your interest to pursue further studies. So quite often, these supervisors may have some funding available from research grants, industry partners, and so on, and they may be on the lookout for a student. So it's quite heavily dependent on approaching the right person at the right time. So don't be disheartened if they don't respond. Just keep trying. Just keep writing to them. And I have to say, like, I do get a lot of queries, especially from our neighboring country, India, where they actually write out like quite like extensively about their interest and so on, about pursuing a PhD in certain areas. And so I suggest that you also proactively approach academic supervisors, express your interest, and sort of hopefully that will also be one avenue into getting into a funded postgraduate opportunity. And other New Zealand universities may have slightly different and sometimes lower entry requirements. So although you might not be in a position to secure a scholarship at the University of Auckland, for example, you might be luckier at the University of Otago or the University of Waikato, for example. So always don't just try for one university. Make sure you try for all options that are available to you. So if you don't meet the UO entry criteria, don't be disheartened. Try for a different university. And also, based on the university's procedures, some universities allow for a supervisor to make exemptions and waive off the requirements, for example. But unfortunately, at the University of Auckland, this is not a possibility. So if you are unable to secure entry, there is nothing a supervisor can actually do about it. But you may have opportunities at other universities as well. So for those of you are thinking about a PhD, your PhD is actually largely influenced by the topic you select, because make sure you select a topic that you actually like, not because an opportunity is available, because for most of you, it is going to define your future career pathway. And also it's going to be something that you're going to be working on for a substantial period of time. So if you don't like it, your PhD experience is actually going to be quite miserable, right? And you also want to make sure, so this is a little bit trickier than choosing an area. You also want to make sure that the supervisor you choose is someone that you can easily relate to, someone you can communicate with easily. So quite often, like we see, like, you know, the supervisor and student are not a good fit, and it might be worthwhile, if you've chosen a certain supervisor, things are sort of progressing, do some background check, like talk to some of their current students. Like these days, it's a lot easier to connect with people around the world and get information. So do make sure that it is a person that you think you can work with. So make sure you're happy with both of these aspects when you commit to a PhD. And yes, the name and the rank of the university may also be important in terms of recognition, employability, the level of facilities that are available to you, and so on. But I would say that this is secondary in comparison to choosing the topic that you like and choosing a supervisor that you can work with. Okay. So some of the things that you might want to keep in mind when you're thinking about postgraduate studies, especially a PhD. So what are the benefits of actually doing a PhD in New Zealand? So this is where I sort of start to do a little bit of marketing on behalf of New Zealand. So all of the New Zealand universities are actually ranked in the top 3% of the world, according to the QS World Rankings. And a PhD gained in New Zealand university is guaranteed to be recognized anywhere in the world. And this is our selling point. Unlike in the UK and other countries, and even Australia, New Zealand actually doesn't charge higher fees from our international PhD students. So irrespective of whether you're a local student or an international student, you will all pay the same fees. But for an international student, there are some criteria that need to be met. Like, for example, you won't be able to stay in Sri Lanka and complete your PhD in New Zealand and also pay the local fees. But apart from that, it's fairly straightforward. Even as an international student, you will typically pay up to somewhere around 4,500 to about 6,300 US dollars as your annual fees for a PhD. So of course, if you secure a University of Auckland doctoral scholarship, this will be covered by your scholarship, or the university basically waives that off. So this is, I guess, a big selling point for New Zealand in terms of attracting PhD students. So if you're unable to secure a scholarship, this is basically what you're looking at spending roughly per year for your fees. Whereas if you were to commit to a master's, unfortunately, this option is not available. So you will be paying about, for example, for a master's in engineering, you'll be paying about 45,000 New Zealand dollars a year, which is significantly higher than this. So if you're able to secure entry into a PhD program, I would recommend that you take it because of the much, much lower fees. So it basically works out to be a lot lower. So as a PhD student in New Zealand, you will have unlimited work rights. So you can work an unlimited number of hours, but we always advise our students to make sure that you balance out your study commitments and your work commitments. But quite often, what we find is our PhD students also tend to work part-time for the university or at a different job quite often. So the university, like depending on the faculty and department, there will be teaching assistant opportunities available, which is actually paid for on an hourly basis. So even if you did have a doctoral scholarship, there is nothing stopping you from taking up a few TA jobs. I did that when I was a PhD student. And as a PhD student, once you complete your PhD, you will be eligible to apply for a 12-month post-study work visa, which enables you to look for a job in your area of expertise. And then if you secure a job and your employer assists you, you're able to then work, apply for a further 2 years of post-study work visa. And quite often in that period of time, people will apply for their residence visas if they've got a opportunity, if they've already managed to employ themselves. And generally, employability isn't it isn't very difficult. So usually, quite often, our PhD students are quite well employed. And if you've got a family, if you've got dependent children, your children will basically become domestic students as far as school fees and things are concerned. So public schools are free for children to attend. So basically all the facilities that are available to a local child will be available to the children of a PhD student, as they will be classified as domestic. And this is one thing I'm not entirely sure about, but I'm fairly certain that as a PhD student, your partner will be eligible to work an unlimited number of hours and enable them to work a full-time job as the partner of a PhD student, which is quite often seen with our PhD students who come in with a family. So I've actually included 2 links here, which has more information on this as well. So feel free to sort of go through this information. There's, of course, there's a lot of information out there in this time and day. So and I'm more than happy to communicate with any of you if you're interested in coming to New Zealand for postgraduate degrees. Of course, my area of interest is slightly different. Like if you're interested in electronics in general, the hardware aspect of electronics, I guess we might be a match. So my area in general is power electronics and electronic design. So supercapacitors sort of fall into the same umbrella. Electropermanent magnet-based designs is something that I also work on. And wireless power technologies. So as you can see, most of these are to do with electronics and power technologies and so on. So if that's something that interests you, please do get in touch with me, and I'd like to hear more from you. And another, I guess, a pet area of interest for me is STEAM education, or science, technology, engineering, arts, and mathematics education, specifically for young children. So this is something that I also like to do a little bit of research on through my undergraduate projects and so on. So at the moment, actually, I've actually been recently awarded a research grant by Facebook to conduct some research in supercapacitor based driven portable electronics. So there are some opportunities that are like currently available with me. So if this is something that you might be interested in, please do get in touch with me. But I also have to warn you, at the moment, the borders in New Zealand are closed, and we are still unsure of when this will actually open up. We're hoping that it will be soon, because our borders have been closed since 2020. So that basically means that they're not allowing any international students to get into the country, which has severely limited our access to students from outside New Zealand, which is a real shame for us as well as for the students. But we are hoping that this will change in the future. But if you are interested in any of these areas, please do get in touch, and I'm more than happy to talk to you. And if it's not something that I am specifically involved in, I might be able to connect you with the right people based on your area of interest. So I guess this is a little bit of further marketing I'm going to do. If you still are not convinced that you want to come to New Zealand, this is what New Zealand actually looks like in most parts, probably not in Auckland, in the middle of the city, but the picture book New Zealand that you've actually like probably seen in pictures and postcards and the Anchor milk packet, for example, that was the picture that I had in mind when I came to New Zealand. So most of these things are from the South Island, but New Zealand is a great travel destination if that's something that interests you. And it's great for the extreme sports lover, bungee jumping and things like that. Commercial bungee was invented in New Zealand, actually. So if this doesn't convince you to come to New Zealand, I don't know what will. So that actually concludes my presentation. I can see that I've gone over time a little bit. Apologies for that. But if we have time, I'm more than happy to take any questions. So please feel free to ask me if you've got any questions. And I can see that there are some questions. I'm only looking at the chat now. So this is actually a really good question that you've asked about can we generate electricity from lightning? So this is actually something that we might be in a good position to collaborate with in Sri Lanka. So like I said, if we by absorbing those lightning surges that we do with the supercapacitor surge absorber, harnessing that energy, we can then deliver that in a useful manner. And that's what we try to do with all these creative applications that we have come up with supercapacitors. So yes, there is definitely an opportunity to generate electricity from lightning, but as we know, lightning is quite random, and it's more common in the tropics than it is in colder countries like New Zealand. So generating electricity from lightning might be more of a project that we can actually do in Sri Lanka, something we can collaborate on actually to basically work in this area. So this was actually something that they were talking about sometime back to sort of work on harnessing lightning energy and making it into a useful form to power things and so on. And the next question that I'm just seeing here is, during which months can we apply for scholarships? So for a PhD, you can actually submit an application at any time. So usually the start date of a PhD is usually the first of any month. So once you've got all of your PhD documents sorted and you start your PhD, usually you start on the 1st of, let's say, October or 1st of November and so on. So there is no cutoff date for applications for PhDs. Whereas for masters, I'm fairly certain that they still do make exemptions, but especially with the Master of Engineering program, the research masters. But you have to start the masters when our academic semester starts. So our first semester here in New Zealand starts generally towards the end of February or the first week of March. So applications for that semester for undergraduate degrees, I know they close in December, but for master's programs, these dates are slightly variable. So even if you see that the applications have been closed for a certain master's program, do email the graduate office, get in touch with them, because quite often they will respond to you and provide you with the right information to guide you. And if there's an opportunity, they will let you submit a late application. So the second semester actually starts in July. So you can always start, some masters taught programs might have other requirements, but the masters for the regular research masters, you can also start in the second semester. So again, applications will close a couple of months before that. So second semester starts in the middle of July after our winter break. So this is the second deadline. So we have, I guess, 2 deadlines for the masters. But like I said, even if it's past the deadline, please do feel free to email them and communicate with them, asking whether you can still go ahead and apply. Okay. Yes, I'm more than happy to provide you with my email address. So I am just going to type it in the chat. And yeah, and if you just go on to the University of Auckland website and type me up, you will be able to find the contact details for me if you lose it in this chat. So just Google my name and you should be able to find me quite easily. Okay? So this is a good question. If a science student needs to do a PhD in engineering, should we go through a master's? So I guess a lot of it depends on the supervisor for that. So if your supervisor is generally happy for you to go ahead, and this will obviously be subject to a screening process as well. So this is quite possible. And I have seen quite a lot of science students go through engineering PhDs. So do you have to go through a master's? If you have a first class honors, generally with your 4-year undergraduate degree, and having first class honors, you are able to get into a PhD program directly. So you will obviously need to submit an application and go through the process. And they will calculate your GPE, and based on that, they will let you know whether you've got entry into the PhD program, or they will give you some alternative options. And in terms of like, will they accept someone with a science degree into an engineering program? I think that is quite highly dependent on the supervisor. You may have one supervisor saying, oh, definitely not, I'm not going to accept that. And then there will be someone who is more willing and more open-minded about it. And I have to say that I have seen quite a lot of Sri Lankan science graduates go through PhDs, especially at the University of Waikato. I know this because my father works at the University of Waikato, and he supervises quite a lot of science students but they obtain a PhD in electrical engineering at the end of it. So yes, it is definitely possible. Okay. Any other questions? So, I mean, if maybe you don't have any questions at the moment, but if you have any questions, now you got my email address. So please do feel free to email me and get in touch with me. And I'm more than happy to support you and help you connect with maybe the right supervisor, because I understand that electronics is not everyone's favorite area. So, but it's not a scary area, I have to say, because I know for a fact, I've got lots of students tell me that they're scared of electronics. Don't be. So if you don't mind working with hardware, but you're just feeling a little bit, maybe not confident, that can easily be resolved. So please do get in touch. So, yeah.
I hope
I'll hand it over to the host now.
Yeah, thank you, madam. I think the time given for the answer session is over, and most of your problems were clarified. Now it's time to pay tribute. I call upon the President of the Physics Society of the University of Sri Jayewardenepura, Mr. Yashan Hettiarachchi, to give away the vote of thanks. Yashan.
Thank you, Areshi. I hope all you can hear me and see me as well. Good evening, everyone. On behalf of the Physics Society of University of Sri Jayewardenepura, I would like to take this opportunity to thank our honorable guest speaker, Dr. Dulsha Abeywardana, for taking her time from her busy schedule for a valuable lecture like this. Through this webinar, we gathered more knowledge on the power of superconductors, and as well as that, the opportunities for postgraduates in New Zealand. Thank you, madam, for this valuable information, and looking forward to a session like this in the future. Next, I would like to thank the Sri Lanka Association for the Advancement of Science, Section E1, for the collaborating with the society to organize the webinar today. I want to thank all of our beloved professors, lecturers, and all the academics who attended today. Finally, I thank all the students and other participants who are gathered here today to grace this event. We believe that you learned a lot today through this webinar, and thank you for giving me the chance, and be safe. Thank you.
Thank you, Ashan. I enjoy the fact that you shared on superconductors and opportunities in university in Auckland, and looking forward to have a session like this in the future. So this concludes today's session. We believe you learned a lot and enjoyed the webinar today. Till then, thank you and stay safe, and good evening.